Today we're doing 4.4 perpendicular lines. So hopefully all of you know what perpendicular lines are. Unlike parallel lines that go side to side and never cross, perpendicular lines do cross, and they cross at a 90-degree angle, right? So just keep that in mind as we talk about perpendicular lines. We're just going to jump right into the perpendicular bisector theorem. So the perpendicular bisector theorem, I'm going to let you guys figure this one out. The perpendicular bisector theorem says if a point is on the perpendicular bisector of a segment, what is true about that point? So for example, we have segment AB here. The red line is the perpendicular bisector. So let's pick a point. So here's a point on that line. What's true about this point? It's also the same thing that's true about this point. What's true about this point? Any point on this line, there's a true fact. So see if you can come up with that. I'll give you a second. So pause. Hopefully you came up with something along the lines of point A and point B, and it's equidistant from A and B, right? So as long as we are on that perpendicular bisector, we're going to be equidistant, right? So this segment here and this segment here are going to be congruent. Okay. There's a few proofs in here. We're just going to kind of breeze through these. But our given information is we have a point P on the perpendicular bisector, and we need to prove that PA is equal to PB. So let's think about a reflection here. What can we reflect across? Well, we can reflect across line M, right? If we reflect point P across line M, where do we end up? Most of us figure out, well, oh, we also line up at point P, right? Point P doesn't move because it's on the line. So the reflection of what else could we reflect across line M? Well, that's point A. We can reflect across line M. That's just a reflection, right? Therefore, we can say that PA is equal to PB because what preserves distance? Well, a reflection, right? It's a rigid motion. It preserves distance. So distance is preserved. That's pretty much all we need to say there. Okay, what conclusion can you make about triangle KLJ? So here's triangle KLJ in the diagram using the perpendicular bisector theorem. So think about this, look at the diagram, look at the marks on the diagram, and see if you can come up with something. So pause. Okay, we can determine that KJ is equal to LJ, right? Or JK is equal to JL because J is on the perpendicular bisector. We know it's on the perpendicular bisector because of this tick mark and this tick mark. These tell us that these two segments are equal, so therefore M is the midpoint. And we know so MJ is a bisector, and we know it's a perpendicular bisector because there's a 90-degree angle there. So we know it's perpendicular. Okay. Moving on. Let's see if we can do 4 and 5 real quick. So I'll pause here for this one. See if we can do 4 and 5. This one just asks us to figure out some measurements. It says ED is 16 and DA is 20. So I'm going to label these 20, and this one is 16. We need to find DC. So what is DC? Well, here's our perpendicular bisector. It's the same as DA. Don't overthink this one. You don't have to do any weird Pythagorean theorem stuff. We can just plug in 20. Number 5, suppose EC, different question. Suppose EC is 15, so E to C is 15. This one's 15. BA is 25. B to A is 25. This one we have to find B to C. Again, it's just the same as AB. So we'll put 25. And there's units on here, I guess, centimeters. Okay. We also have the converse of the perpendicular bisector theorem. So the converse of the perpendicular bisector theorem, we're just going to jump right into this. It is remember the converse, we switch the if and then statements. So why does it do that? I don't know. So if we have an if then statement, we switch the if and then part. So the first part here, what's it? There you go. Yep. So the last one said that if there was a point on the perpendicular bisector, it was equidistant. This one goes the opposite. So it says if a point is equidistant from the endpoints of a segment, right, then it is on the perpendicular bisector. So we've just switched those up. There's this thing. There's a proof in this book here. It's called an indirect proof, where instead of proving this theorem, right, this converse theorem, what we're going to do is we're going to assume that this theorem is false, and then we're going to try and prove it true. And when we get to like a logical conundrum, right, that like 1 equals 2, or something is not equal to itself, or something like that, then we know that it can't be, the false version can't be true, right? So it's like this weird double negative. They're not the strongest type of proof, and in fact, I'm not even going to go over it. I'm just going to point it out. It's this proof here. It's example 2 in your book. If you do it, if you fill it out and it's correct, I'll give you some extra credit. Power to you, but we're not going to do it because it's just too complicated. Too much brain power. If you have lots of brain power, though, you should definitely try it. See if you can do number 7. So pause. Okay. This one, however, where you say AD is 10, BD is 6. This one asks us to find the length of AC. It's a bit of a trick question. Since we know that BD is a perpendicular bisector, we know that this segment is equal to this. So I can put a little tick mark here. I'm putting double tick marks because there's already single ones there. I know that DC is also 10. So whatever this value is, I'll just multiply it by. We can use Pythagorean theorem to figure that out. Right? A squared plus B squared equals C squared. And we know what C is, we know what B is, we just don't know what side A is here. So I'll leave A squared, and then I'm going to add 6 squared, and that's equal to 10 squared. A squared equals 36 plus 36. Okay. Plus 36 equals 100. A squared equals 64. Therefore, A equals, what's the square root of 64? Well, it's, I would put 8. Man. All right. What am I thinking? Why did I put 6? 6 and 6 is 36. 64. A squared is 8. Yes. What's wrong with 8? Yes, we're at 8. So A is 8, right? This length is 8. Cool. So that gives us 8. This length here is also 8. So then the length of AC is 16. So hopefully that's what you got. Yay, 16. All right. This one, I want you to go ahead and try and figure this one out as best you can as well. Or follow along. These are actually in your book. It's filled out, but I want to kind of go through it like it's a whole new proof. Because we need practice on proofs. Each proof is unique. We can't just do 5 proofs and then figure out, oh, this is what I do for every single proof. We have to kind of come up with each proof individually. However, there are some patterns. Like, for example, we always start with the given. Right? So the measure of angle 1 equals 90 degrees. This is what we're proving, though. It says if 2 lines intersect to form one right angle, and they're perpendicular and they intersect to form 4 right angles, right? So all these angles are 90 degrees. So if we're just given one of these angles being 90 degrees, we have to prove that they're all 90. So we have to prove angle 2 is 90, angle 3 is 90, angle 4 is 90. So first up, we're going to say that angle 1 and angle 2 are a linear pair. How do I know that? Because that's given, that's in the figure. They're also supplementary. How do I know that they're supplementary? Well, I've proven they're a linear pair. Therefore, this is the linear pair theorem. Angle 1 plus angle 2 equals 180. That's the definition of supplementary angles. Sure. And then this one says 90 degrees plus the measure of angle 2 equals 180. Well, that's kind of weird. How did I get there? Well, I switched out this angle 1 for 90. Am I allowed to do that? Yep, because they're equal. And that's called substitution property of equality. Finally, that gives me the measure of angle 2 equals 90 degrees. What did I do to both sides here? Well, if this were an algebra problem, I would say minus 90, cancel, minus 90, go. So I've subtracted from both sides. So that's the subtraction property of equality. And then finally, that got us here. The measure of angle 2 equals 90. So we have angle 1 and angle 2. So we're good there. Angle 2 is equal to angle 4. Well, how do I know that? It's a vertical angle. Angle 1 is equal to angle 3, also vertical angles. Therefore, the measure of angle 4 equals 90. How do I know this? If angle 2 is 90, and if 90 equals angle 2, and angle 2 equals angle 4, therefore angle 4 equals 90. I would say transitive actually works a little better, but substitution works as well. So either way there. Here's another one. These paragraph proofs, you can think of them more as like a plan for a proof or just an explanation of the reasoning. I am not going to require paragraph proofs. I like the 2-column format because it's very clear what are the statements, what are the reasons. But here's a paragraph proof. We'll go through this one. It says if two intersecting lines form a linear pair of angles with equal measures, so here's my my line here. Oops. And they form a pair of linear angles. So here's my linear angles. And the angles are equal, then it says the lines are perpendicular. So all I'm given is that the measure of angle 1 equals the measure of angle 2, and I need to prove that the two lines are parallel. So by the diagram, angle 1 and angle 2 form a linear pair, right? A linear pair is when I have a line that's cut by a ray, and that forms two angles. So angle 1 and angle 2 are supplementary using the what theorem? Linear pair theorem. That means they add up to 180. Why? Because that's the definition of supplementary angles. It is also given that, what else could we figure out from here? And in fact, it will lead us to figuring out that the measure of angle 1 plus the measure of angle 1 equals 180. So what did we do? This looks pretty familiar with here. With this thing here, we've switched out this angle 2 and angle 1, right? So the other given information is angle 1 is equal to the angle 2. Therefore, we're able to switch these out using the substitution property. So we have angle 1 plus angle 1 equals 180. We can just rearrange this and say it's 2 times angle 1 equals 180. And therefore, the measure of angle 1 equals 90, just by dividing by 2. Since angle 1 is a right angle, we can say that L is perpendicular to M using the, in this case, just definition of perpendicular lines, right? Perpendicular lines form 90-degree angles. That's all we need to know there. Okay. We're going to just give this one. The theorem in part B, the converse would also be true. So we can keep that in mind. Okay, go ahead and see if you can do number 9 here. Oh, cool. It's a toothbrush again. In this case, we know that angle 1 is 50 degrees, right? So I can label that. That's 50 degrees. Measure of angle 5 is 90. So measure of angle 5 is 90. So I'm just going to mark that with a right angle mark. Now we need to find angle 4. We know that B and D are parallel, right? C and E are parallel. So we have two pairs of transversals that are, or two pairs of parallel lines that are cut by transversals, right? If we just ignore B and D for a second, I just want to show this one. Okay. so I'll ignore that information. Just ignore B and D totally. I know that this angle is 50, therefore I can conclude some other information, right? I can say that this angle is what? It's going to be supplementary, right? So 130. I know that this one is 50, right? I know that this one here is 130. So that's all information I can get just from that, right? I'm going to move these. Okay, and now I'm going to look at this pair. So I'm going to look at this and this cut by my transversal. I know that this one here is I know that this one here is what, 50, right? No, 90. So this one's 90. So, and this is 130. So therefore this part here must be what, 40? And they form a vertical pair. Here's my vertical pair. Therefore, angle 4 is 40 degrees. This is just one possible way to solve this. There are many other ways you could do this. We could do some other pattern. I think the book uses one totally different than the way I just did it. So keep that in mind. However we want to get over there is fine, but we need to somehow set up this relationship with this angle and get it down here to angle 4. Many different options to do that. Okay, that's it. Good luck on the problems.